In today's lab, we'll essentially be measuring the strength of a weak acid, except it's a really interesting weak acid that actually has several protons to give up. Or in other words, we say that it is polyprotic. Phosphoric acid actually has 3 different protons it can give up as an acid. First, it loses a proton to become dihydrogen phosphate, then another to become just hydrogen phosphate, and then another to become just phosphate. Each time, it becomes more and more difficult to lose these protons, because the conjugate base becomes more and more anionic, but exactly how difficult does it become? In other words, how strong are each of these conjugate acids? Well, each of these processes has an equilibrium constant associated with it, which tells us what the ratio of concentrations of products to reactants must be. The bigger this ratio, the more likely it is that the molecule will give up its proton, and the stronger the acid. It's as simple as that. So we'd like to know what the ratio is, which is otherwise known as the acid dissociation constant or the ionization constant of the acid. To measure it, we can make use of the famous Henderson-Hasselbalch equation. This equation states that the pH of a solution of a weak acid is equal to the pKa for that acid, which is just the negative log of the Ka, plus the log of the ratio of the concentrations of conjugate base and the conjugate acid. So for us, this could be the following. We could solve for the pKa, and hence the Ka, just by measuring the pH of the solution, which is easy enough. The only problem is that we might not know the relative concentrations of our conjugate acid and base. But the good news is that if the concentrations of conjugate acid and base were equal, the ratio would be equal to 1, and the log of 1 is just 0. So we just need to somehow measure the pH when we're reasonably sure that the conjugate acid and base are at the same concentration. So how will we do that? Alright, let's imagine what will happen to the pH of a phosphoric acid solution as we slowly add some strong base to it. We start with a solution that contains about 100% phosphoric acid, since it's a weak acid and therefore doesn't give up its proton readily. If we slowly add some base, like NaOH, some phosphoric acid molecules will be forced to give up their proton and turn into dihydrogen phosphate. Sooner or later, as more phosphoric acid molecules turn to dihydrogen phosphate, their concentrations will balance out, and we call this the half neutralization point, since half of the phosphoric acid has been neutralized. This is exactly when the pH will tell us what our pKa is. But let's keep going. The pH isn't changing much here because we've created a buffer. This solution has molecules of both conjugate acid and base available, and therefore can absorb other acids and bases pretty effectively. This region of the curve is generally referred to as the buffer region. Sooner or later, however, we add enough base to exhaust the supply of conjugate acid and the pH sharply rises. This is what we call the equivalence point, since now we've added an equivalent amount of NaOH to the amount of phosphoric acid that we have started with. Continuing on, we'll now be turning our dihydrogen phosphate into hydrogen phosphate and approaching yet another half neutralization point. This would be the point at which our concentrations of dihydrogen phosphate and hydrogen phosphate are now the same and will also give us our second pKa value. Since there are 3 protons to lose, there are essentially 3 steps to this plot, and we'll be left with something that looks like this. So, to figure out our acid strengths for each of the phosphoric acid and dihydrogen phosphate, we simply need to plot our data and find those half neutralization points, since we know that pH is equal to pKa at these points. All we'll need to do is calculate the inverse log of the pKa to get the Ka, and we're done. Before we get started today, you'll need to calibrate the pH meter. To do that, a buffer solution that has a known pH of 7 is provided. Place the pH electrode in that buffer solution and press the Cal button followed by the up or DN buttons until the screen reads 7 pH, like so. Next, press the Yes button and the screen will read Ready. Press Yes to accept and then Yes once more when the screen reads SLP 100. One more Yes, and we're all done and ready to use our pH meter. The burette and pipette that you'll use today must also be cleaned before starting. See the appendix in the back of your lab manual for more details on that. Pipette 25 ml of the phosphoric acid solution into a clean 250 ml beaker. Then add 50 ml of deionized water so that there is enough liquid to immerse the pH electrode. Place the beaker on a magnetic stirrer and add a clean stirring bar. Lower the electrode so that the tip is below the surface of the solution and make sure that it is clamped securely in this position. Now, this next part is very important. Make sure that the stirring bar can turn without hitting the electrode. Obviously, if the stir bar continually hits the electrode, you run the real risk of significantly damaging the equipment. At this point, you can fill your burette with standardized NaOH solution and adjust the level to around 0 milliliters. Get your burette mounted in a good spot so you can make additions directly to your beaker and record the initial pH. Add about 1 ml of the NaOH solution. Record the precise volume and the resultant pH. Continue with these 1 ml additions of NaOH solution and keep a record of both the resultant volume according to the burette and the corresponding pH. As the endpoints are approached, and spoiler alert, they'll be about 21 ml and 42 ml respectively, make smaller additions of the NaOH solution. Continue these additions until well beyond the second endpoint. It will be helpful and speed things up a lot if you plot your data as you collect it. Plot pH on the y-axis and the volume of NaOH solution added on the x-axis. Use a pH range from 1 to 12 along the longest side of your graph paper, so you can expand the spacing of the pH axis to give a more accurate plot. If you're unsure about what to do, refer to the appendix in your lab manual for instructions regarding how to construct the graph properly. Alright, so now to handle your data. After you've plotted your experimental titration curve, you should have something that looks somewhat like this, although you may not have quite as pronounced of a third step on the top. We need to find the pH at the first and second equivalence points. To do that, we carefully draw parallel tangent lines along the first two buffer regions. When we're satisfied that these lines follow our buffer region data well and are parallel, we measure the distance between them. Let's call it d. Now we find the point on our curve that crosses exactly 1/2 of d. The volume at that point is the volume of NaOH at the first equivalence point. So that must mean that at exactly half of that volume, you'll find your half neutralization point. By tracing that point up to your curve, and then to the left, you find your pH at the half neutralization point, which as we saw earlier is exactly equal to the pKa you're looking for. To get the second pKa, all you need to do is add the same amount of volume from the half neutralization point to the volume at the first equivalence point. Then, just trace up to your curve again, and then to the side, to determine your second pKa. The lab manual says to evaluate these to 2 decimal places, so take care in plotting your data accurately. Then determine your Ka values by taking the inverse log of your numbers. Also, don't forget to display how you've evaluated these pKa's directly on your graph for when you hand it in, being sure to show the midpoint of each titration. On the reverse side of the plot, give an explanation of how you determine each of your pKa's and the calculation of your Ka's, and you're all set. Enjoy the lab and be safe.